Hello again. My name is Lewis McIntyre, and I'm here to talk to you about the Hubble expansion using the velocity triangle to develop very simple graphical solution that explains why, through simple geometry, an observer anywhere in the universe will see all other bodies receding from him with their velocities a function of their distance. Let's see why that is. The Hubble expansion was developed by Edwin Hubble in the 1920s. He used Cepheid variable stars, relatively common stars with distinctive periods, but relatively identical intrinsic brightness, to measure the distances to 46 galaxies, up to 326 million light years away. He observed that each galaxy had a down Doppler shift to the red end of the spectrum due to a receding velocity proportional to their distance. This proportionality h0 is the Hubble parameter, now taken to be between 67 and 76 meters per second per megaparsec, a megaparsec being equal to 3.26 million light years. It was initially assumed to be a constant, but as we gained the ability to measure galaxies at much greater distances, h sub o was determined to be itself a function of distance, increasing for the more distant galaxies. This led to the concept of the expanding universe related to the subsequently developed Big Bang theory of the creation of the universe. Let's see if we can make this expansion more comprehensible using the velocity triangle. At the time of the Big Bang, all matter was imparted its proper velocity of the speed of light, defining its own unique direction of time, uniformly distributed in all directions. Thus, at any proper time, the entire universe resides on the surface of a four-dimensional sphere, expanding at the speed of light from O, the Big Bang, the ultimate point of collocation. Each body has its own unique direction of time based on its initial direction as modified by subsequent collisions or gravitational interactions with other bodies. But we can't observe any star until that star's light has reached us from that body. We observe the star at time A equal to c cap t, the age of the universe as measured on Earth, and determine the location of the star to be at time B, which is c cap t minus x, at a distance x at c. Since the star and the Earth share a common point in time, specifically the ultimate t equal to 0, the Big Bang at O, we determine that the star is moving with velocity v over c equal to x over c cap t minus x as shown, increasing for stars of greater and greater distance. And the Hubble parameter is likewise increasing with distance. For small x, the Hubble parameter is approximately 1 over the age of the universe, as originally determined by Hubble, based on the distances measured 100 years ago. The proper time of transmission, the age of the universe measured by the star's clock when the light we observed was emitted by the star, is determined by computing the invariant, measured time squared less the measured distance squared, to obtain the equation shown after some simplifications. The relativistic Doppler shift of the light is along the path dBA, equal to 1 plus V over C divided by the square root of 1 minus V over C quantity squared. This becomes the equation shown when we insert the definition of V in terms of C cap T and X. Note that an odd thing happens as X tends toward just half the age of the universe as measured on Earth. V over C tends toward 1, the speed of light. The proper time of transmission tends toward 0, and Doppler shift tends toward infinity. Why is that? So what is the age of the universe? This example is a measurement of a star moving at half the speed of light at a distance of 6.9 billion light years. A faster star moving at 70% of the speed of light is more distant at 9.8 billion light years, and one moving at 90% of the speed of light is still further at 12.42 billion light years. But light did not leave the star 12.42 billion years ago, equating to C cap T minus X equal to 15.38 billion years after O. That's our clock. Light actually left the star at the proper time D, equal to the invariant square root of our measured time squared, less our measured distance squared. This was the age of the universe as measured by the emitting star when the light we now observe was actually emitted. In this case, 6.7 billion years after the Big Bang. This will get smaller with increasing distance and associated velocity, tending toward 0 as the distance becomes half of C cap T. The reason is that the locus of our successive measurements of that body lies on the world line of constant velocity V equal to the ratio of X over C cap T minus X. Thus, whatever C cap T we choose as our time of observation, this defines X. If we observe an object receding at nearly the speed of light at 13.8 billion light years, it took, in our reference frame, just over 13.8 billion years for that body to reach the point we assume is the time of our transmission, making the universe twice as old as the farthest object we can see, or 26.8 billion years. If we went back 13.8 billion years, we would still see that object at 6.9 billion light years, still almost half the age of the universe at that time of observation. The cosmic microwave background radiation emitted 379,000 years after the Big Bang maps to a three-dimensional sphere surrounding us at nearly 13.8 billion light years distance. In other words, the Big Bang is not a point behind us. It's a sphere surrounding us. Does our simple calculation yield the correct value for the Hubble parameter? So we have developed a very simple model of the Hubble parameter in the expanding universe. As the Hubble parameter is expressed as kilometers per second per megaparsec, and our expression is percentage of the speed of light per light year, we must do some unit conversion. We simply multiply our expression for h by the speed of light, and again by the conversion of megaparsecs to light years, to find that the initial value of the Hubble parameter is 36.5 kilometers per second per megaparsec for values of x very much less than the age of the universe. Doubling to 73 kilometers per second per megaparsec as x approaches 13.8 billion light years, half the age of the universe. This compares with recent measurements that give a range of 65 to 75 for the more distant bodies. To validate this model, we identified 12 galactic objects with documented distances from 6.4 to 13.37 billion light years distance, with redshift expressed as z from 0.545 to 11.9 as shown in the table. These are plotted on the accompanying graph as solid triangles. Since I feel that the observed redshift is much more reliable than estimated distances, particularly in the extreme range at nearly 13.8 billion light years, I chose to determine the velocity triangle distances that give the measured redshift. I plotted results as the solid line on the graph. The velocity triangle gives excellent results at the distant end to within a few percentage points. The predicted distances follow the fall-off toward the nearer distances, beginning at 12 billion light years, but tends to overstate the distance thereafter by up to 25%. This may be due to the fact that the expansional component of these velocities is half the speed of light or less, and proper intrinsic velocities may introduce more uncertainty in the observed redshift. This shows how the velocity triangle solves for measured and proper events for 3 of the selected galaxies. Measured times and distances are shown as black stars, all of which lie on a light line connecting to the time of observation. Their proper times of transmission, when the light we are observing was emitted, are Doppler shifted to the time of observation at A. The oldest galaxy we see from this list is at a distance of 13.72 billion light years with a recessional velocity of 99% of the speed of light. This corresponds to a proper time of transmission of just 2.14 billion years after the Big Bang. The youngest galaxy in this set is somewhere between 6 to 8 billion light years away, with a recessional speed of 40% of the speed of light, and a proper time of transmission of 7.8 billion years after the Big Bang. So in summary, the velocity triangle provides a simple model with excellent results without invoking general relativity or dark matter to explain the changes in velocity over time. The universe is expanding, but in the direction of time, not space, and at the speed of light. The Big Bang maps to a sphere surrounding us rather than a point behind us. Therefore, if mass is uniformly distributed around us, except for the nearby galaxies, gravity will have no effect on our trajectories, as we are being attracted equally in all directions. If you want to learn more, see my other videos on this channel, or buy my book, Writing on a Light Beam. It's available on Amazon, or you can buy a signed copy through my website shown. And thank you for watching. Please press the like button. It helps YouTube to make this material more available to others. I hope you got something out of this, and please have a very nice day.